Now we see a couple of images that both depict kinetic energy. Kinetic energy is the energy of movement. If something's moving, it has kinetic energy. So, which of these which of these scenarios depicts the greatest kinetic energy? Now, you may instinctively say that the car racing down the road has more energy, more kinetic energy than the soccer ball that the man is kicking, and you would be right. So, what factors do you use to determine that? Uh, the the car is moving fast, so the factors you would use are the mass and the speed. The car has a lot more mass, so it takes more energy to get it moving. And it's probably moving just by the image, we can infer that the car is moving much faster than the soccer ball. So to get something moving at a higher speed, it also takes more energy. Here we see a visual depiction of the effects of mass and velocity. In image A, we see an object of mass. We'll just say that's a mass of one because there's one block. A mass of one moving at a speed. We can see the speed indicated by the length of the blue vector. Remember the magnitude of the vector. I guess that's velocity. The magnitude of the vector tells us, or the length of the arrow tells us the magnitude of the vector. So we see a arrow with a length of one, and so we see it has 1 unit of kinetic energy. In image two, we see that if we double the mass and keep the same speed, we also double the kinetic energy. However, in image C, we kept the same mass, so we still have a mass of one, but we doubled the velocity. We know that we doubled the velocity because we see that the vector, the arrow, is twice as long. Well, if we double the velocity, then we get 4 times as much kinetic energy, not just twice as much. Kinetic means related to motion. So kinetic energy is the type of energy associated with an object's motion. Remember that velocity had a bigger impact, or a change in velocity had a bigger impact on the kinetic energy than a change in mass, or than an equal than a change in mass of equal magnitude. Double the mass, you double the kinetic energy. Double the velocity, you quadruple the kinetic energy. All objects that are moving, whether it's a soccer ball being kicked, a speeding car, like we saw a couple of slides ago, falling skydiver, exhaled air molecules, they all have kinetic energy. Anything that has mass and velocity has kinetic energy. So the amount of kinetic energy that an object has depends on its mass and velocity, but these properties affect the amount of kinetic energy differently. So, based on what we learned on the last slide, which quantity, when doubled, has the greater impact on an object's kinetic energy? The answer is velocity, because the equation for kinetic energy, and you're definitely going to want to write this in your notes, the equation for kinetic energy is Ke equals 1/2 times mass times velocity squared. So if you double the mass, you just double the kinetic energy. If you double the velocity, then you have to square that change in velocity, and you get actually 4 times as much kinetic energy. So since a velocity is squared, any change in velocity is also squared. And so a change in velocity has a bigger impact than a change in mass. You may see this equation written as K equals 1/2 mv squared, or as E equals 1/2 mv squared. Kinetic energy is not always depicted by Ke. Think about what happens when a firework rises into the sky. And I'm talking specifically about the path that the firework follows before it explodes. And we see this on the right side. It has kinetic energy. Why does it have kinetic energy? Where does the energy come from? And where will it go? Well, a firework suddenly gains kinetic energy, which propels it upward into the sky. This kinetic energy comes from the forces that lift it from the ground. It can be a quick explosion, like in the case of a mortar launched firework, or it can be a burning of a propellant, like we see in this image on the slide, where the fireworks have a small engine on them that burns and launches them up vertically, or close to vertically in this case. As the firework rises, it loses kinetic energy, and that's why it's slowing down, but it gains potential energy. It's getting higher, so it gains potential energy. If it is not burned out by the time it hits the top of its arc, it has potential energy based on its position in the Earth's gravitational field. We already learned about how position in a field, in a force field, can uh, impact the kinetic energy of an object, right? We talked about the orbits of planets. When a planet is farther away from the sun, it has more kinetic energy. When a firework is farther away from the Earth, it has. I'm sorry, I just said that wrong. When a planet is farther away from the sun, it has more potential energy. When a firework is farther away from the center of the Earth, it has more potential energy. So then the firework, if it hasn't exploded, it starts to fall, and as it falls, the potential energy changes back into kinetic energy and it speeds up. The energy of the explosion is then released by chemical reactions that take place between substances that are stored in the shell of the firework and gases in the atmosphere. So the energy of the explosion, the spectacular explosion we see, is not really related to the kinetic energy that lifted the firework up there in the first place.